Once upon a time, there were two of many ways to describe a physical system. The first approach involved following individual particles as they move through space. This approach to describing a physical system was known as the Lagrangian approach. The second approach involved looking at a region in space known as the control volume and tracking property changes across the boundaries of that region. This approach was known as the Eulerian approach. The Navier-Stokes equations were a way of analyzing a physical fluid system through the lens of the Eulerian approach. But wait, you may be saying, didn't you just say there were two approaches to describing a physical system? Why did the Navier-Stokes equation use the Eulerian approach? And it's a good question. Let's look at an example. Say we had water flowing through a pipe, and we wanted to know the velocity at which water exited the pipe. In the Lagrangian approach, we would follow the velocity of each fluid particle, of which there could be billions or more. In the Eulerian method, however, we only need to analyze the average behavior of the fluid at the boundary in space where the fluid enters and exits our chosen control volume. In order to obtain the bulk fluid behavior in the Lagrangian method, the individual fluid particles must be tracked. Tracking the position and properties of many particles can complicate the analysis when a person is trying to extrapolate the behavior of the bulk fluid. On the other hand, drawing a control volume whose boundaries cover the inlet and exit of the pipe and only analyzing the properties at the boundaries through the Eulerian approach gives us the bulk fluid behavior through the computed property changes across the control volume, which is an often much simpler analysis.